Okay, so there is another advertisement. So somebody asked me whether it's written somewhere and even written in Russian. That's a very good question, because I can show there is a book which is written indeed in Russian, and unfortunately that we haven't translated it. We have only translation of the first half and in an old version, but in Russian it's more or less it's printed as is, so it's finished by definition, and it's freely available. You can use it, find the file in the internet, and even I brought some copies. So if for example, if there is somebody who doesn't use the computer, I will give as a gift to. I hope there is at most one person with this property. Is there anybody who doesn't use the computer in ordinary life? Of course, not for something, but just okay. So you can get the book later. Okay, so now again I want to summarize what we did before. So first, we defined for every function d, we defined the complexity like this. Complexity with respect to this d. Then we proved that if we have two, they are kind of similarities. So there is a definition when d is better than another one, when the complexity is smaller, maybe up to a constant. Then we proved that they form similarities. So for every two decompressors, there is a one which is better than both. And then we restrict our attention to computable decompressors, and then the set has a minimal element, and this is optimal. It's called optimal decompressor, and it has the minimal complexity. And the last thing which I should say, that then complexity of the optimal decompressor is just called Kolmogorov complexity. It's not exactly defined, because there are different Kolmogorov complexity functions corresponding to different decompressors. But any two Kolmogorov complexity functions differ by O of one additive term. So Kolmogorov complexity is really not a function, it's just a family of functions. But we can say that we fix someone arbitrarily and then we use it for all purposes. But still it's a kind of cheating, because really there are many of them.
The constant depends on the compressor.
Which constant?
This one. So
no, of course, if we have two decompressors, we have some constant which is different, and it depends on both decompressor actually. So it may happen that for one is better and for other is better, but the difference is bounded and by a constant which depends on both decompressors.
There is no global constant by which every two decompressors can.
Yeah. So that's a question to all of us. So maybe the question is, can one find a global constant which bounds the difference between any two Kolmogorov complexity functions? What do you think? No. Why?
We can add any constant number of bits without independent of x to optimal decompressor.
So, for example, we can, here is the answer. Let's take an optimal decompressor, and let's agree that in a new version of optimal decompressor, every program is just the same, but we need to add million zeros before. And with this new decompressor, the complexity will be just exactly a million bigger, because we use this million zeros. So we can make it artificially inefficient, still having it optimal, because the optimality is defined up to a constant. So we cannot find a constant which is good for any.
Artificial decompressor will be still as optimal as the previous one.
No, it's as optimal as yes or no thing. Either you are optimal or not. You don't. There is no kind of classification.
So it will also be optimal.
This new crippled decompressor will also be optimal because we carefully use only constant overhead to get it. Now there is another reason. For each specific string, we can make a specialized decompressor which is optimal, but for this specific string gives a very short description. And so there are many reasons why it's not possible. Okay, so let's try to prove some things, but maybe we'll start with easier thing. So first thing, for every n, there exists an incompressible string of length n, which means that there exists some x of length n, and Kolmogorov complexity of x is greater or equal than n. So we fix some optimal decompressor, and then we don't write it here. So here we assume some optimal decompressor, but we just write it like this. So why for every length, there is a string of this length which has no shorter descriptions. How do you prove this? It's obvious why. Yeah, so we just try to count how many string of smaller complexity we have. So there is only one string of complexity 0 because there is only one program of length 0. So complexity and number. Complexity is equal to 0. We have at most 1. Maybe less if it's not, the compressor is not defined on empty string. Complexity 1, we have at most 2 strings of length 1 because there are 2 programs of length 1. And with complexity n minus 1, we have 2 to the n minus 1. So in total, complexity less than n, we have at most 1 plus 2 plus 2 to the n minus 1, which is 2 to the n minus 1. So there exists at least one string which has complexity n. And generally, you can say that the number of strings x of complexity less than n is less than 2 to the n. Yeah. And it's related to a question which is very good for high school students and philosophers and other people. So there is a... sorry. There is a question, a kind of a story. Imagine that somebody, I don't know, some mega software company sends an advertisement which says that they invented a new kind of compression method, new compression method, which allows you to compress every file by at least 10 persons. And the question is, should you believe this story or not? So assuming that the compression is claimed to be lossless, of course, if you just erase some part of the file, then it's easy to do this. So they claim that there is a lossless compressor which allows to compress every file, say 10 persons. So why it's impossible, how you will say? Oh, first, of course, you can iteratively compress it farther and farther, but actually it's not exactly the contradiction, because then you need to know how many steps you need for decompression. So if you compress it a million times and then you have this compressed program, it's not enough to reconstruct the thing, because you need also know this million thing. Because you don't know, you can decompress it once, twice, and so on, but you never know when to stop.
You would compress it once, twice, and so on, while you something shorter than one thing.
Okay, let me put another thing. Imagine that this company comes to you and makes a demonstration. They want you to buy the software. And for this, they say something, advertise it like this. They tell me, give me a file of 1,000 bytes, and if my program will not compress this file at least by 100 bytes, then I will pay a large amount. So imagine that the representative of this company comes with such a claim. And you are lucky to be in this audience and to profit from this, how to say it, strange, in Russian there is a word oferta, but I don't know how to say it in English. Just offer. No, maybe it's not exact translation. Okay, anyway, you want to benefit from this stupid salesperson who is ready to pay the money if you suggest some file which this program cannot compress. So how will you win? What you will do then? Sorry?
Take a random file random bits.
Yeah. So what you should do, you don't know actually the decompressor. The compressor is somewhere in his computer, so you cannot test in advance. But what you can do, you can try a random file, take a say 1,000 random bytes, which is 8 random bits, and then give it for compression. And so the probability that it will successfully do this is just the number of strings of complexity less than, so if it's 100 bytes, then it should be 800 bits, so it should be is at most 2 to the, and total number is, so the probability that you will not get the money is, no, not 1,000 actually. It's a bit worse. I was too optimistic. 2 to the minus 800. So it's a good chance of winning. So with probability 1 minus this, you win, and so this universal compressor probably will not work on your file. Okay, so now we know that actually, if we want to write a picture, there are all strings of length n. And then there are some simple string, one string of complexity 1, 0, 2 strings of complexity 1. So we get some kind of family which becomes bigger and bigger, and then, but even if we go up to complexity n minus 1, they do not cover the entire space. There are some incompressible strings. Okay, so this is just the quantitative picture. So any question up to now, or it's clear? Okay, and next thing which I already promised, why there's a bad news, why Kolmogorov complexity is not computable. We have a computable functions for very simple decompressors, but if we take the universal decompressor, then we get a non-computable function. It's not computable. So can anybody explain why? Sorry? Oh, in a sense, we can go in other direction. We can prove this, and then reduce the halting problem to this somehow. It's actually easier. Okay.
Let us assume that we can
Yeah. Yeah, that's a very natural idea. So imagine that let K be computable. So we want to get some contradiction from this assumption. So how can we get this contradiction?
Diagonalize.
Okay, so how do we diagonalize?
The description of the language of the function that computes K.
Okay, there is some description, of course, computable by some machine M. Good, so what? Machine has some description. So what do we do then?
We will write such a program that will pick 1, then 2, and so on, sequentially all numbers.
Yeah.
When it finds the number that has Kolmogorov complexity more than complexity of this program, we will just output that number.
But we don't know the complexity of this program in advance.
Well,
Okay, but just let me say, write down what you wrote. For every number I, if we can compute this Kolmogorov complexity, then for number I, we can find a minimal, the first, if in some order, lexicographic order, first bit string of complexity at least I. So we know that there's only finitely many strings of given complexity. So if there are we have infinitely many strings, so at some point we can find a string of complexity greater than I. Yeah. So what? What is the contradiction?
Let us create another function which does approximately the following thing. It takes a bit string, runs the machine M on this bit string to calculate the complexity.
Yeah.
And if this complexity is smaller than the length of the string, it returns this complexity. And if it is bigger, it returns the number of bits in I.
Okay, so what is so bad in this?
Just I. So somehow we have created a function which for every I is better than Kolmogorov complexity.
No, we need to create a decompressor. It's not just a function. Okay, let's look at this first bit string of complexity greater than I. So what can we say about this about the complexity of this string? Yeah, so what is the complexity of the first bit string of complexity greater than I? So there is I cannot translate it again in English, but there is a standard question in Russian, сколько стоит пятикопеечная булка? And so what we know that the complexity of this string is greater than I. It's not a big deal. But also it's smaller than something. How can we specify this program, this string using some, yeah?
Let's consider this function as a decompressor.
Okay, this function is also a computable function, so it can be considered as a decompressor. Yeah, so it may be not optimal decompressor, but it's still a decompressor. So
Let us replace I by I times 2.
but where should we replace? Just here?
Yes.
Okay, why not? Let be 2i.
Yes. Then we know that the complexity is not greater than I plus some absolute constant.
So we can say that complexity is, on the other hand, is not doesn't exceed I plus some constant, because in our decompressor, when I is a argument, we need only to specify I. But actually, this is a small error in this argument. What is the error? To specify I, how many bits do we need? Actually, we don't need not I bits. I is a number, and so and we measure the length of the bit string. So it's actually will be a logarithm of I approximately. So and we don't need 2I actually. We can forget about this. Oh, not so easy to forget about this too. And so for big I, we get a contradiction. Contradiction for large I's. So this is a proof that Kolmogorov complexity is not computable. And actually, there are two comments on this proof. So you know that people in logic are just trying to make theorems from paradoxes. And this theorem is, for example, from Russell paradox, you get a Gödel incompleteness theorem, if you heard about this. But this is another theorem which we can get out of some paradox, which is called Berry paradox. And the Berry paradox is just like this. The integer by and you can get what I should write here. It's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. No, actually, I'm not sure I'm correct, because in English language, sometimes they like to have some there or a or something. Maybe there is something wrong here. But still you can get the idea, and you can correct it. If you know English, you can correct it to a correct one. So it's exactly, so this minimal integer cannot be defined, but still is defined. And like here, this is the first bit string which cannot be defined by a program of length less than I, and here is still this program. So we get a contradiction exactly of these things. And this is the Berry paradox. And we can even, actually, if we look at our result, we can say that complexity function doesn't have, is not computable itself, that doesn't have a computable lower bound. Because if it had a computable lower bound, then we can use this computable lower bound instead of the function and still get computably a string of complexity greater than given I. Of course, we want to have computable lower bound, not non-constant, not O of 1. O of 1 bound we can have, but how to say, unbounded lower bound is not possible, because then we can find a string of given complexity.
What about the upper bound? Is
Ah.
the upper bound bounded by its own length?
Yeah. Upper bound, that I should say earlier. So we know if we have the identity function, we know that complexity of every x is just the length of x. This is what we have seen. And since we have our optimal description should be not worse than this identity description. So it should be bounded by identity complexity of x plus some constant, which is x plus constant. But of course, some constant is unavoidable. We cannot require all the string have exactly this complexity, because we don't have space for descriptions. If we should use an exactly zero length for zero string and one length for one string, we just have some permutation. So it's not good.
About then this is the Shannon entropy.
So the question is, imagine we take a random string of length n and take, let's try to, what is uniformly random? So what will the expected value of complexity? So we know that complexity of random string x, expected value of complexity. So we know that complexity is bounded by length. So of course all the values will be bounded by x plus constant. So it all will be bounded by x plus constant. But what will be the, now we are interested in the average value of complexity for strings of given length. So what do you think it will be? So the guess is just the kind of absolute majority will have a close complexity. So we can say that the theorem, this is also greater than n minus some other constant, not n, x minus other constant. And, oh, what a strange thing. Length n. Okay, how do we prove this? Yeah, so let's see how often we have some decrease. So complexity decrease by k units is possible if the complexity is less than n minus k. And then probability of this event is O of 2 to the minus k. So expected decrease is bounded by the sum k to the O of 2 to the minus k. And the sum O of the sum k 2 to the minus k. And if you studied calculus, you know that what the sum is. But, sorry? No, if you studied calculus, you really know what is this constant. But by the way, how do you compute the constant? Imagine you want to compute it precisely. How do you do this? So this is the sum s. So if you just s plus the sum of 2 to the minus k, it's just sum of k plus 1 2 to the minus k. And let's write like this. And so we get some equation when we can find the exact value of this constant. But it's rather clear that this exponential thing is converged even if we have some k factor. So it's just O of 1. So most complexities are close to n. So if we want to write draw a distribution, then somehow all things are, here we have 0. Oops, strange idea. So here we have exactly 0. And most of the things are concentrated here. And here we have very exponentially decreasing thing. So it's distribution, the histogram of complexity of strings compared to length and complexity. But this is if we consider the union distribution. And what you asked is a more complicated thing. Imagine that we have some kind of, we take, I don't know, p is equal to 2/3, and let's take a coin which is non-symmetric, coin which is 2/3, 1/3. And then we make a random coin tossing with this non-symmetric coin. We get a random string of length n, but now it's not uniformly random. It's random with respect to this distribution, so strings with more zeros are more probable. And then we can look at the average complexity, or we can try to draw a similar picture. So we have now not a fair coin, but we try to make still the same experiment. We make a coin tosses, get a string, and measure its complexity. So what will we expect? What will be the average complexity? Sorry? It will be just n. It's not so obvious, but the answer is n times the entropy of this 2/3, 1/3 distribution. So it's a bit less than n. And let me just say informally how things. Now we have still the same absolute bound. So we have complete zero here, and then we have some point around entropy times n. And here things are concentrated here, not absolutely, but very sharp around this point, and then they decrease again back here. So somehow this is now the entropy is concentrated of a typical string will be near this. So it's very important if you want to win this, if you start to make a coin tossing to get money from the software company, you should be very careful that your coin is symmetric. Because if your coin is not symmetric, then there are good chances. For example, if it's not so non-symmetric that this entropy is less than this price bound, then probably they will take into account this non-randomness, and they will still be able to compress this thing. So you should be very careful. Okay, so this is mathematical statement, and you can think about this statement. It's not so obvious, but let me be more. It's late today, and you should in 10 minutes you should go to the excursion. So let me end with some philosophical things. So there is a philosophical. Philosophers always like to think about Gödel theorem. And Gödel theorem, at least at the level of philosophers, is that not all true statements can be proved formally. So proved in some formal system which has strict rules how to prove things. And there is, now we can prove it easily, the theorem. There is a kind of Gödel theorem in Chaitin's version. So not all, we can be more specific. Not all true statements of form complexity of some string is greater than some number. So let's consider only very specific, special kind of statement. Not Fermat theorem, not in any kind of conjecture, but just statement that some complexity of some string is greater than some number. And then not all the true statements of this form can be proved formally. Formally proved. And probably you see now why it's true. What will be bad if they all can be proved? So imagine we have some proof system which proves, of course it should prove only true statements, otherwise not a good formal system. But imagine we have a formal system which proves all true statements of this form and only true statements. How can we get a contradiction? Sorry? Imagine we have such a formal system.
We can compute k because we can use just binary.
Oh, we can compute k and make binary search, but just we can say that instead of our argument, we can map I to a first string that is provably has complexity provably greater than I. Yeah?
It's even unnecessary because we could just use it to obtain a computable law of R. That's it.
Okay, just we can wait. No, it's not really a computable lower bound. What is computable lower bound?
Why? I mean, we can enumerate all the proofs.
Yeah, but we never know when we get the best lower bound. No, you need a special argument because you can have upper bound also. You can wait until they mix. Okay, but anyway, this is the simple result by Chaitin, and that's even very promising because usually the Gödel theorem says that there is something true which is not provable, but it's a rather delicate thing how to get this Gödel statement. But now you know how to get statement which is probably true, which is practically sure, you can practically sure to be true, and still it's not provable. Just toss a coin a million times, get a specific string of zeros of ones of length 1 million, or you can get the string from the internet. They made some experiments like this and write down this thing, and write a statement saying the complexity of these things is greater than, I don't know, if this is million, you can have 500,000. So this is, and this is a string coin tossing. And then you can be practically sure that the statement is true, because we know that to get, in coin tossing, get something which has smaller complexity is very improbable. But still, you can be sure that you cannot prove it in formal arithmetic, because, no, you can, there are some discussions what is the formal arithmetic. The axiom should be rather simple, so there are technical things still. But still it's a way to get a new axiom. So it's philosophically important because it's a way to get a new axiom which is true but not provable. So we can, every of us can extend our formal arithmetic by some new axiom being sure that they're true. So this seems to be a good idea, but actually it's not so powerful as it seems. These axioms are true, but most of them are completely useless also. And, but there is an interesting question. I still, one of them related to this, one of them is still open. For which strings the statements are powerful, for which string the statements of this form are powerful, for which they are not. Though they are interesting things, but it's another story. I can, of the axiomatic power of the statements, an interesting story, not clear completely now. So this is this is an open problem which is related to rather simple things. Okay, so are there any questions about today's proof or whatever? Yeah?
Concerning this philosophical part.
Yeah?
Are there any numerical estimations? Can we have a function which estimates which answer such queries for some relatively big share of strings?
Which computes complexity?
Which of course, is a partial function.
Yeah.
That either compute answers these inequalities truly, or give no answer, and for which the domain is related with it.
Okay, so can we construct a lower bound which is computable and defined on a reasonably big domain?
Yeah.
No, just the same problem. If it's defined on big domain, then sometimes the value of this lower bound should be big, because otherwise it's bounded, so it's not interesting. And so if we have a lower bound, which is an unbounded lower bound on any domain, then we can use it instead of we don't need actually to compute the complexity of every string. We just try to get this lower bound for different strings. As soon as we get a string of complexity greater than I, we stop. So this will be a program which is also computable in I if the function is unbounded. and we get the same kind of contradiction. We get a string complexity greater than I, but to specify the string, we need only the log I bits plus some constant depending on the program.
So the domain should be of somehow logarithmic size.
No, domain should be, no, domain can be of any size, just the lower bound which is provided should be finite all the time. So we cannot get any non-trivial lower bound in this way. It's even, but if we allow the lower bound sometimes be incorrect, we can just say that for if a string has length n, we can say n minus 100, and for most of the strings it will be correct. But for some strings it will be not correct. So this is not the complete lower bound. Okay, so then we should, last thing I should ask, what you prefer for tomorrow. So there are several possibilities. We can speak about more philosophical applications, about random sequences of infinite length, of also connections with Shannon entropy, and these things. And another possibility is to speak about applications to some proofs. So for example, there is a very funny, there is a incompressibility proof of some special case of Lover's local lemma. So there are even simpler examples, and we can start with simpler examples. So just as a part of advertisement, you can find the proof. The proof, if you didn't understand completely what Mario was explaining today in this book, you can find it's written in Russian and with a minimal amount of formulas. So I think it's understandable. So we can go into this direction, application to existence proof. But probably we should make a choice what you prefer. So, second part.
Philosophy.
Oh, God. Okay, who wants philosophy? Okay, and who wants proofs? Okay, proofs are better than philosophy. Philosophy you can do yourself easily. It's not a problem. But proofs are more complicated. Okay, thanks.